All right, so we'll get started. So I have homework number A assigned online. It's due again Tuesday. Okay, so that's next week. For in-seat classroom disinfection, I assigned to Austin and Jared for today. Okay, so so for the third exam, it's probably going to be after the Easter break. Okay, so we'll have another homework due in the week. We'll have Easter break, and then after you guys come back from the Easter break, we'll have exam 3. Okay. All right. So last time we talked about induction. So basically, if you have a magnet, if you move it in and out of a coil, then you actually generate EMF, the voltage in that coil, or current if it's a complete circuit. Okay, and then you can do also in this fashion if you have a primary circuit that has coils. As long as there's current changing in the primary circuit, then you'll induce the current in the secondary circuit in the coil there. Okay, so that's because in either cases, you will have magnetic flux changing in the coil. So magnetic flux is defined as the B field, the magnetic field times the area of that coil times the cosine of theta, where theta is the angle between the B field, magnetic field, and the normal direction of the coil. Okay, so in that case, you can see you can have either magnetic field changing or the area of the coil changing, or in some cases you can have the direction of the magnetic field and or the angle with the magnetic field and the normal direction that makes the two makes it changing. Okay, so any of those three changing in quantity would cause magnetic flux changing. Then you will have induced field. You will have induced the current in the coil or induced EMF. Okay. All right. So the amount of the voltage induced in the coil, we call it induced EMF. That's equal to minus of M. M refers to the number of coils you have, times the change in flux over change in T. So it's the rate of flux changing, okay? Delta phi over delta T. All right, so the minus sign in the equation comes from Lenz's law, which says the induced current always flows in the direction that opposes the change that caused it, okay? So that's in the direction that opposed to it, okay? So, and then you can use right-hand rule to here to determine what would be the current direction that induced in the coil if you have the magnet going in towards the coil or away from the coil, okay, in those two cases. And we also took a look at eddy currents, which is the current induced in the conductor if the conductor is moving in the magnetic field. Okay, so then you'll have eddy current changing that. So this is again, it's effect of and the Lenz's law. So then the induced current will be having effect that is opposed to the motion that caused it. Okay, so in this case, if this metal piece is going down, then the force will be opposed to it. Okay, so it'll be in the upward direction. So that's the magnetic force this eddy current will be experiencing. All right. So in the previous cases, we see the area is not changing, but you have changing magnetic field strength. So then flux will be changing. Now in this section, when you have actually magnetic field is not changing, but if you have the area changing, then flux is changing. So then you'll have induced EMF in this closed circuit over here, made by the two rails and this moving rod over here. Okay. So the result is you will have induced current in the rod or in the circuit, then there's the light bulb here will be lit in that case. The induced EMF epsilon that should be equal to, now if you have just one coil, then it's equal to B, the magnetic field, times the speed of the rod is moving times the length of the rod, okay? And because of that, you have voltage induced in the rod, then there will be electric field in the rod, which is equal to the magnetic field times the speed of the rod is moving. Okay. Now, because you have induced current inside the rod, so the rod is carrying current. It's also in the external magnetic field. So this rod will experience magnetic force. The magnitude of force is equal to I times L times B for a current carrying conductor. And then in this case, you can calculate what's the current here will be the induced EMF BVL divided by R. Okay, so times L times B. So the result will be the magnetic field square times the speed times the length of the rod square over R. Okay. And you can also calculate what's the mechanical power. If you want to maintain the rod with the constant speed of V, then you need to add an external force to it. Okay, so the force times V is going to be equal to, this force is the same as the magnetic force that the rod will be experiencing. So it will be B square V square L square over R. On the other hand, you can calculate what's the electric power that's produced by the induced current. So BI squared times R, and this is also B squared V squared times L squared over R. So you can see basically if you are pulling the rod with a constant speed V, then you are converting that mechanical energy or mechanical power into electrical energy or electrical power. Okay. So those two are the same. That's because this one is simply being converted into the electrical power. Right? And then we were about to take a look on the example on this one here. It says the figure below shows a zero resistance rod sliding to the right on a two zero resistance rails separated by the distance L equal to 0.500 meters. The rails are connected by a 10 ohms resistor, and the entire system is in a uniform magnetic field with the strength of 0.750 Tesla. Find the speed at which the bar must be moved to produce a current of 0.175 amps. Okay, so you have resistor. This is 10 ohm here. This length, or this length is 0.5. Okay, L is 0.5. B field is 0.750 Tesla. The current going through the rod is 0.175 amps. That's the same current as the going through the resistor because this is a closed path, closed circuit. Okay. All right. So it's asking you what will be the speed. Okay. So you guys can see if you can solve for this, and then we can take a look at the solution together in a couple of minutes. Okay. All right, so in this one, we are given the magnetic field, we are given the length L, the resistance, the I, okay? So you are looking for the speed V. Now, this equation will relate your speed V, okay? So the induced EMF um, by a moving rod with the speed of V is equal to B times L times V, okay? So you're looking for V, you need to know BL and epsilon, but epsilon is not given, okay? So then we need a second equation to figure out epsilon, okay? According to Ohm's law, the current is equal to the voltage divided by R, okay? So the epsilon will be the voltage on the resistor here, because the rod is acting like a power source, okay? So it's moving rod will have induced EMF in it, so that's you can treat as a power source or battery or some power supply. So in that case, it tells you I, it tells you R, so epsilon can be calculated, right? Epsilon will be equal to I times R, then I times R is equal to BL times V, so then you can isolate V, so that would be I times R over B divided by L, okay? So you have those four quantities given. You plug in your numbers, divided by the B field here times the 0.5 meters, the length of the rod, okay? So that gives you 4.67 meters per second as the speed of the rod that is moving, okay? All right. Let me know if you guys have any questions about this one. All right, so if you are clear, we then can turn to the next section. So next section talks about electric generator. So basically, an electric generator actually convert mechanical energy into electrical power energy. Okay, so for example, if you have wind turbine as the electric generator, so basically wind will drive the turbine, so then the turbine will be moving. So that's a form of mechanical energy, and then there will be a magnetic field inside it. So then use that to convert the mechanical energy to electrical energy. Okay, all right. So there's always an outside source of energy used to turn the coil, which is the mechanical energy. So maybe in a sense, there's multiple ways, multiple processes here going on. Okay, so if you have a coal a power plant, then basically you burn the coal, so which is converting the chemical energy, okay, into heat, and then the heat is used to boil the water, okay. So and then the steam will drive turbine in that case. So there's in real electric power plant, there's multiple process there going on. For another example, will be nuclear power plant. So you are converting the nuclear reaction energy, then use the heat from there again to boil the water, okay, and then the steam will drive the turbine, okay. So in that case, but the final step is always from mechanical energy to electrical energy, okay. All right, so just quick review on the magnetic flux, okay. So if you want to generate electric power or induce EMF, then you would have change in magnetic flux, okay? So again, as I mentioned last time, you can have either changing the magnetic field or changing the area of your coil or changing the angle between the magnetic field and the normal direction of the coil. So for the electric generator, you are actually using the last variable here, theta. So you'll be turning your coil, so then the angle the magnetic field makes with the normal direction of this coil is always changing, okay? So B is fixed, B field, magnetic field is fixed, okay? You typically have magnet that has south pole and north pole facing each other. And then this coil usually is a fixed shape, okay? So you not be able to change its area, but the only thing you can change is the angle between the magnetic field and the normal direction of the coil. So that's the case over here. Okay, so you are changing the angle here to change the magnetic flux, then to generate the electricity. Okay. Now, if you are driving the coil with a constant speed, then in this case, this angular speed will be constant. Okay, so then the this term, the b times a times cosine, okay, so then it will be a cosine function for flux, okay, it will be cosine function. And then for the rate of flux changing, all right, it should be actually a sine function, okay? So for those of you have taken calculus, you know if you do derivative to a cosine function, it gives you a sine function, okay? Or you can do in this manually, you can draw a cosine function and then you can take the slope at a few points and then make a new plot. You will also see that, okay, without using calculus knowledge, you'll see that the result will be uh, sine function. Okay, so then for electricity generate, it's going to be a sine function. Okay, so it's equal to n number of turns of coils you have times the magnetic field times the area of the coil times omega, which is the angular frequency. That's how fast the coil is been turning. Okay, sine of omega t. Okay, where omega is equal to 2 pi times frequency, or 2 pi divided by period. Okay, so then this will be the electric voltage generated, okay, as a sine function. It will have a maximum value of when the sine is equal to 1. So sine has a range from -1 to +1, right? And the rest four quantities, they are fixed quantities. So then you expect that those to be fixed number times a range. Okay, so you'll get the maximum. So the maximum induced EMF or induced voltage is equal to number of turns times the magnetic field strength times the area times the angular frequency, omega. Okay. So if you have maximum voltage and then the voltage changes as a function of a sine function, right? So then we'll use the root mean square quantity v of v sub rms, okay? That should be equal to the maximum voltage divided by square root of 2, okay? Now, in the US, the household voltage is 120 volts, okay? So that's referring to the RMS voltage, okay? The root mean square voltage, okay? It's not a maximum voltage, so your maximum voltage will be higher. And because of that, for electric generator, it generate voltage as a sine function. So you can see for half of the time, the voltage is negative. Half of the time for voltage is positive. So you are actually having alternating current in the circuit. So half of the time your current will go in one direction and then half of the time it will go in the other direction, okay? That's why it's called alternating current. All right, so let's take a look on one example here. It says a rectangular coil, 25 centimeter by 45 centimeter, has 150 turns. This coil produces a maximum EMF of 75 volts when it rotates with an angular speed of 190 radians per second. In a magnetic field of strength B. So what's this strength B? So it tells you maximum. Okay, we can start with listing the knowns here. So it tells you the maximum induced EMF, that is 75 volts. Okay. Now, maximum induced EMF should be equal to number of coils times the B field times the area times the angular frequency, or this is also the same as the angular speed. Okay, so angular frequency is angular speed. All right, so we know number of turns of coil N is equal to 150. The areas, I think we also know it, is 25 centimeter by 45 centimeter. Okay, and then omega, the angular speed, is given as 190 radians per second. Okay, so this is the same angular speed as we talk about when we have angular rotational motion. Okay, angular motion or rotational motion. So that's angular speed. Also refers as to angular frequency here. This is another thing, but I would like to mention here maybe. So for angular frequency is equal to 2 pi times the frequency. Okay, so then for the household power electricity is 60 hertz. That refers to the 60 hertz frequency. So the angular frequency should be 2 pi times 60 hertz. Okay, so when you have a question like that, just keep in mind angular frequency should be equal to 2 pi times the frequency given. Okay. All right, so let's take a look on this one here. We are looking for the B field. So we know this guy. Okay, so we know this, we know this, we know this, we know this. So we can solve for B field. Okay, so on this one, to solve for B field, you will rearrange the terms you have. So it'll be this maximum epsilon divided by number of turns times the area times omega. Okay, so then this would be 75 volts divided by 150 times 25. This is centimeter by centimeter, so you want to convert it into meters first. Okay, so times 10 to the minus 2, and then multiply by 45 times 10 to the minus 2 meters. All right, and then the angular frequency is 190. That's already in SI unit, so you can just take that down. All right. Looks like I forgot to calculate what's this, but we can do this quickly. You can also do that on your end. So 75 divided by 150, and then 0.25, 0.45 divided by 190. Okay. So this would be 0.0234 in Tesla. All right. Any questions you guys might have? All right. So if not, then we'll move on here. So we have talked about the electric generator. Now, we also use electric motors a lot, right? Like the toys, like toy cars, etc. So this is the other way around. Okay, so it's the opposite of electric generator. So basically, in this case, you will have a power supply to the coil here, and then this is placed into a magnetic field inside it. Okay, so then if you have power supply over here, then there will be torque on the size of the coil. Okay, so then the magnetic field, because each side will experience force, so there will be torque, then will be drive the circuit. Okay, So then the coil here. So then the coil will be attached to a motor, a drum like this. So then it will drive this. Okay. So then mechanical power will be taken at the output over here. Okay. So this is the other way around. All right. Okay. Um, so then the next section here, let's take also a quick look on this one here. It's on back EMF. Okay. So basically, if you have an electric motor, we can see here. So the current here will produce the torque on here. So then this guy will be moving. Okay. Now, because this is moving, the coil is moving, then this is again will be an electric generator, right? Because then you will generate electricity in that sense. Okay. So that's again, it's kind of Lenz's law. So it's opposed to the change of it. So then the equivalent or the result of this will be you'll have a back EMF generated. Okay, so then you'll have a voltage generated opposed to the um, electrical input source voltage. Okay, and then this typically less than, for example, if this the driving EMF is 120, then this is less than that. So it's in the range of from 0 to 120. Depends on the speed of this coil is moving, okay? But it's in the opposite direction of it, okay? So that's called the back EMF, okay? All right. Any questions you guys might have on back EMFs? So if not, we'll move on to the next section, talk about transformers, okay? So I don't know if you guys have seen this, but you might have seen this like the high voltage transmission lines, okay? So from the power plant, electric power plant, so actually the voltage coming out of it usually is much higher than what we are using. Okay, now this is not a figure referred to us in the US, but could be well in certain European country, they are using 240 volts. Okay, a lot of countries are using 240. Okay, so then if you travel, in addition to yeah, this is something interesting. So a lot of countries are using different voltage. Okay, so 240 or 220. Now also a lot of countries have different outlets as we have here. So if you go to European countries, you need to also have the outlet adapter, okay, because they are having the same shape. So we couldn't just plug in our power cord into the outlet. Okay, so make sure if you are traveling, check on that. Okay. And then usually for the laptop or cell phone chargers, you don't need a transformer to convert that voltage into 120 because usually it has a range of can take from anything from 100 to 240 or so. Okay, but for other electronics, you might want to check on the voltage that can take. Okay. Anyway, so for here, for the power plant, usually it comes out with high voltage. Then when it's being transmitted to the household before that, usually it travels long distance, right? We can be using the electric power from, say, from, I don't know where, but maybe from Colorado. Okay, so it travels long distance here. So for that purpose, its transmission of electric power through long distance is via the high voltage. Okay, so if you have high voltage, then the dissipation of energy on the way is smaller. Okay, because the dissipation is based pretty much consumed by the resistance of the transmission lines. Okay, so then transmission lines has R that as fixed. So if you want to reduce the dissipation, you want to reduce the current while it's being transmitted. Okay, so then I here should be much small So in order to reduce I, you want to raise the voltage, okay? Because the power provided by a power plant is fixed. Power is equal to V times I, okay? So if V is large than I is small, then I squared times R during the transmission of electricity from a power plant to the consumer end, then will be small, okay? So that's why high voltage is used. All right, but anyway, before it gets to the household, there will be a step-down motor transformer to bring the voltage down here. All right, and then from here, it will be further reduced to the say 120 or 240. Okay, here for the household here to be used. Okay, so these are called transformers. They change the voltage, okay, from one value to another. You can have the voltage go up, then the transformer is called a step up transformer. Okay, you can also have a transformer that brings the voltage down. It's called step down transformer. Okay. All right. So for a transformer, this is what it looked like. Okay, it has this metal piece, ferromagnetic material. Okay, and then it has coils on one end, and then also coils on the other end. Okay, so if this is a step-up motor, then the primary coil will has less number of turns than the secondary, because on here the voltage will be smaller, and then over here the voltage will be larger. That's because of the flux change. Okay, so flux change here and here will be the same because this is a ferromagnetic material. So B field generated by this coil, okay, because this is the input here primary. So then you have current going through here, and B field here will be the same as B field here, okay. But you have more number of turns over here, then flux over here will be more than the flux going through this side of the coil, okay. So basically, and this is the equation. So the voltage on the secondary coil is equal to minus of N times delta phi over delta T according to Lenz's law. Okay. In the primary coil, it's the same. Vp is equal to minus N, but primary delta phi over delta T. Now delta phi and delta T are the same here on the secondary and primary. So then you can set up the two equation, or you can relate the two equations. So then Vs over V, or Vs over Ns will be equal to Vp over Np. Okay, because from the first equation you can see Vs over Ns is equal to minus delta phi over delta T, and then from the second equation you can see Vp over Np will be equal to minus delta phi over delta T. So Vs over Ns will be equal to Vp over Np, or Vs over Vp is equal to Ns over Np. Okay. So the voltage ratios between the secondary circuit and then the primary circuit is equal to the number of turns coils in the secondary over the number of turns of the primary coils. Okay. In a circuit, so this, if you see this symbol, then it refers to a transformer. Okay, so this is the symbol for transformer. You can kind of see this. This is one coil, and then this is another coil with two lines in between. Okay, that's the sign for a transformer. All right. So then in that case, so P from the primary coil is equal to I PVP, current in the primary times voltage in the primary. Okay, that should be equal to IS times VS times PS. Okay, so if we can ignore the dissipation of energy throughout the transportation, then that's true. Okay, so if that, then with this equation, the power in the primary equal to the power in the secondary, and combine that with this equation, then we can find the relationship between the currents in the secondary and the primary circuits. Okay, so IS over IP then will be equal to inverse of the turns of coils. Okay, so IS is actually basically IS times NS will be equal to IP times NP. Okay, you can do cross multiplication in that sense then. Okay, so then this is another equation for a transformer that you can use. All right. Let's take a look on this example here. It says electric motors in a toy train requires a voltage of 4.5 volts. Find the ratio of turns of primary coil to turns on the secondary coil in a transformer that will step the 120 volts household voltage down to 4.5. Right, so basically you need an adapter or a transformer for that. Right. So here we're looking for the ratio of the primary coil's number of turns over the number of turns on the secondary coil. Okay, so then in this case, this should be equal to the voltage on the primary over the voltage over the secondary. Okay, so you can simply do that if when you take down the transformer equation. So this will be 26.67. Okay. All right. Let me know if you have questions on this one. Okay. So there's a question about the unit of this one. So this one, we will not have units because we are looking for the ratio of the turns of coils. Okay, so then there's no unit on this guy here. All right. All right. So let's move on here. Electric safety. So we have talked about the electrical hazardous of two hazardous could be possible: thermal hazardous or shock hazardous. Okay. Now to prevent shock hazardous, there's another approach we can do is we can have the appliance grounded. Okay. So usually for large appliance, you see there's a ground wire on the power cord. So that will ground the appliance to the ground there. So in case there's um, breakage over here, so the voltage may be in contact with the outside case of the appliance. Now, because the appliance, the outside case is grounded through the power cord, okay? So then the current will go through here, going to the ground here, instead of going through your body, okay? So this is what a ground line look like, okay? That's the green line that is being connected to the outside cases of the appliance, okay? So in the case of if you accidentally touch the outside case of it. Okay, so if you are grounded through this here, so then um, the high voltage might go through your body. But if the outside case is grounded, okay, so this is the case that if it's not grounded, okay, so if this is the case, if the case of the appliance is grounded, so then the voltage will go through the wire, okay? Now we know that the current prefer to go through low resistance route, okay? Than going through your body. Your body has a resistance that's much larger than the wire, okay? So then the voltage will go through the wire or the current will go through the wire to the ground instead of going through your body, okay? So that's why ground lines are used, okay? All right. Any questions before we move on to next section? Inductance. Okay, so if we have a circuit like this, now if we have a coil here, that's several turns of wires here. So when you have element like this, we call this as an inductor because the moment you turn on the switch, now there will be electric current going through here, and there will be magnetic field generated. Okay, so then you have flux changing in that case. Okay, if you have magnetic field generate, then there's magnetic flux, and this will be in the will be tend to oppose to the reason that caused that change, right? So then this is similar. So then there will be induced electric voltage inside the coil, which will be opposing to the cause of it, which is the battery. Okay, so then um, for the induced EM here on here, you can replace with a battery, which will be in the opposite direction as this guy for the terminals. Okay, so the positive will be against the positive, the negative will be against the negative. Okay, so this is called induced or back EMF for the coil. Okay, so then there's a response of this guy to the signal added to it, just like for a resistor, if you have resistor inside here, there's a response of if you apply voltage across it. Okay, so we call this as an inductor. All right. And for the induced EMF or back EMF in this case, that's equal to the number of coils you have there, or the number of turns of coils you have there, and times change in flux over change in time t. So the rate the flux is changing. Okay. Now the flux is changing. That is proportional to the current. Okay, changing because the flux is equal to B times A times cosine theta. In this case, B is changing, A and theta is not changing. Okay, and B is changing proportionally to the current. Okay, so then you can also relate it to the rate of current changing with a constant we call L. It's called inductance. Okay, so in that case, you can see L then will have a unit of equal to voltage on the very left end here divided by the current amps and then divided by time t. So it becomes times S. So 1 volts times second divided by amps. It has its own name called Henry or H for the symbol. Okay, so for the inductance, right? So L is equal to, from this definition over here, is equal to delta phi over delta I, because delta t and delta t can cancel out if you take this part of the equation. Okay, so delta t cancel out, and L equal to n times delta phi over delta I. Okay, and for a solenoid, it has many turns of coils in it. Okay, so then for a solenoid, we learned in the previous chapter that the magnetic field inside the solenoid is equal to mu naught, the permeability of the vacuum, a constant number, times n equal to the total number of turns you have divided by the length. Okay, and then times I. So this is number of turns per meter. So in that case, the magnetic flux can be calculated as n times A times B times A, and then cosine of theta, that in that case will be 0. Theta is 0, cosine theta is 1. It's going to be equal to mu naught n squared I times A times L. Okay, so this comes from, you can rewrite M, capital N, as small n times L. Okay, so then small n times L times B, which would be this guy, mu naught n I. Okay, so then you have two small n's in it. Okay, so mu naught n squared I times L and then times A. Okay, so that's the expression for magnetic flux there in the solenoid. So then the inductance for a solenoid is equal to phi, the total phi divided by I, okay, because inductance is equal to n times phi, change in phi over change divided by change in I, okay, divided by change in I. So then if you start from 0 to the final I, okay, this is what you get, okay. So mu naught n squared times A times L, and then I will be divided already. Okay. Now, in this case, we have already the capital N total numbers of turns over here. Okay, so N is already included, so we don't have another capital N here. Okay. So we basically have this N already included in this. So the phi magnetic flux is already N times of it. Okay, so then that's there already. All right, so then for the inductance of inductor, which is the solenoid. When the solenoid is in circuit, we call it inductor. Okay, so then that's equal to mu naught n squared times A times L. All right. Now let's take a look on if you have an inductor inside the circuit. So then what happens there? Okay, so you will have then current going through it. Okay, so when you have current, then you will have a magnetic field generate inside the inductor or the solenoid here. Okay, so then if you have a inductor here that is in the circuit with a resistor, now this is somehow look like a RC circuit. Okay, so it's actually doing the same thing as an RC circuit. So you will then have energy stored in the inductor as a form of magnetic field, energy stored in the magnetic field. Okay, when we have a capacitor, you have energy stored in a capacitor as the energy stored in the electric field. Okay, so in this case, that's the same here. So for induced EMF in the inductor is equal to minus L delta I divided by delta T. Now we can use Kirchhoff's loop rule here. So going through the whole loop here, you will end up with the voltage change being 0. So starting from here to here, when you cross it, it's positive, and then when you go here through the resistor, it's negative. Okay, and then going through here, this is the induced EMF there, minus the, L times delta I over delta T. That equals to 0. Okay. So from loop rule over here, if you multiply the left-hand side of the equation by I, all right, then it will still be equal to 0 because left-hand side should be equal to 0. Okay. So in that case, you can see epsilon times I minus I squared times R minus Li delta I over delta T should be equal to 0. Now, the epsilon naught times I is voltage times I. So this is having a dimension of power, right? It's voltage times current. This will be giving power. I squared times R will be also power for a resistor, okay? So then this term should have the same dimension as power, okay? So this term then is the power of the inductor, okay? So this is the power that is in the inductor. All right, it's Li delta I over delta T. And power is defined as the energy, change in energy over change in time t, right? So then let's write this as change in energy, U as energy, but in this case, it's the energy in the magnetic field, okay, sub m. So that means magnetic field over delta t is equal to this guy, the power in the inductor, Li delta I over delta t. Now you can see delta t and delta t will cancel out, so then change in energy is equal to Li times delta I, okay? Now this next line might be looking something intimidating to some of you guys, but it's just doing integration of it, okay? So if you have learned calculus, you know then this is the result. But if you didn't learn calculus, you just need to know the result over here. You don't have to, you will not be asked to do an integration, okay, in the class. But this is how mathematically the energy stored in an inductor is derived, okay? So energy in this inductor is equal to 1/2 Li squared. L is the inductance of it, I squared, okay? L will be a constant, I will be the current, okay? So energy stored in an inductor will be equal to 1/2 Li squared. And if we take a look on the magnetic field in the solenoid, which is inductor, so that's equal to mu naught M times I. And also for the inductance, we derived this a couple of slides back, and this is mu naught N squared times A times L, okay? So then 1/2 the energy stored is equal to 1/2 Li squared. That's what we got in the previous slide. It's equal to 1/2 of this guy, and then times I squared. You can write I from this here. So I will be equal to B over mu naught times N. Okay, so B over mu naught times N, that's your I, and then you squared it. And the result would be, so N here, you square N here, so N squared and then N squared will cancel out, okay? There's 1 mu naught here, there will be 2 mu naught in the denominator, so then you have 1 mu naught remain as the denominator here. You still have 2 there. You have B being squared, and then AL, okay, goes there. So the energy stored in the solenoid, which is the energy stored in the magnetic field, is equal to magnetic field squared times the area, cross-sectional area times L, divided by 2 times mu naught, okay? And the cross-sectional area of the solenoid times the length will be giving you the volume of the solenoid, right? So this is the volume of it. So then you can divide both sides of the equation by volume, the very left hand by volume, that will give you energy per volume, means energy density, should be equal to B squared over 2 mu naught, okay? Yeah, let's take a look on this one first. So energy density then will be just equal to, this is the volume, is equal to A times L, okay? So it will be equal to magnetic field squared divided by 2 times mu naught. And this might be looking familiar to you guys because when we talk about energy stored in the electric field, it's equal to the electric field square divided by 2, but I think it's epsilon naught divided by 2 times the E field, okay? So let's see here. For energy stored in the capacitor, which is the energy stored in the electric field, that's what we derived several 2 or 3 chapters back. Energy density in the electric field is epsilon naught times E squared over 2. Okay, so which is similar to this guy here. Okay, just this is in the denominator, the other one has epsilon naught in the numerator. Okay, so basically energy stored in the magnetic field should be proportional to its field strength square, and then the same for energy stored in the electric field. Okay, should be proportional to the electric field strength square. Okay, we'll stop here and then we'll come back on this example next time. Okay.